Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss the zeroth law of thermodynamics. So our topic is the zeroth law of thermodynamics. Idea is like this. Last time we defined adiabatic and diathermic walls. One ideal separation was adiabatic wall and the second one was diathermic wall. Adiabatic wall was perfect heat insulator and diathermic wall was perfect heat conductor. And in case of adiabatic wall, we said it is approximated by thick asbestos. Thick asbestos. And in case of diathermic wall, we use thin metal wall. I repeat their definition. We said if two systems are separated by adiabatic wall and we make change in the macroscopic variables of one system, that will not affect the macroscopic variables of other system. And in case of diathermic wall, if two systems are connected by it, changing macroscopic variables of one system will change the macroscopic variables of other system. And when two systems are separated by diathermic wall, they are said to be in thermal contact. Now, using these definitions of adiabatic wall and diathermic wall, we're going to state the zeroth law of thermodynamics, and first we will understand it. Now, for example, I have two systems, system 1 and system 2. And let these systems be constant volume gas systems. Constant volume gas systems. What is the meaning of that? That means these are two gases which are kept at constant volume. That means constant volume gas systems. And let they be isolated from each other. And you know the meaning of isolation. There is no exchange of matter or energy taking place between the systems and their surroundings. And another thing, if they are constant volume gas systems, we know in that case, increase in temperature is indicated by increase in pressure of the gas. What we do, I will draw this diagram. This is my system 1. This is my system 2. And I separate them from each other. Let this be diathermic wall, and this one be adiabatic wall. I repeat, I have two systems, system 1 and system 2, which are isolated from their surroundings and from each other. They are constant volume gas systems. Now what I do, I bring them in thermal contact with each other. That means I separate them by diathermic wall, and I isolate both the systems from their surroundings by adiabatic wall. Now what will happen? In general, the macroscopic variables of these systems will change until the systems are in thermal equilibrium with each other. What is the meaning of that? That means as I bring them in thermal contact, macroscopic variable means here pressure. The pressures of both the systems will change in general until they come in thermal equilibrium with each other. The pressure of one system will decrease and the pressure of other system will increase. So when they are in thermal equilibrium with each other, these macroscopic variables will stop changing. When it stops, we see they are in thermal equilibrium with each other. Now, if it's also possible that when I bring them in thermal contact with each other, nothing happens. It's also possible that their macroscopic variables will not change when I bring them in thermal contact. I connect them by diathermic wall. If in that case, these systems were already in thermal equilibrium with each other, that means it is possible that system 1 and system 2 is isolated from each other and they are still in thermal equilibrium with each other. So to test that, we bring them in thermal contact using diathermic wall. If macroscopic variables doesn't change, they were already in thermal equilibrium with each other. And if they change, they will come in thermal equilibrium with each other after some time, right? Now another thing, now if I have, first I will make a statement. Statement of Zeroth Law of Thermodynamics is two systems in thermal equilibrium with a third system are in thermal equilibrium with each other. This is the statement of Zeroth Law of Thermodynamics. What does it say? It says two systems in thermal equilibrium with a third system are in thermal equilibrium with each other. That means if I have system A, system B, and they are in thermal equilibrium with the third system, system C, they will be in thermal equilibrium with each other also. I will make a diagram. Let this be system C, A, and B. So let this be adiabatic wall. So A and B are isolated from each other. And let this be diathermic wall. That means system A and system B both are in thermal equilibrium with system C because they are thermally connected. But from each other they are isolated by adiabatic wall. Now if I bring these two systems A and B in thermal contact with each other, this is my system A, system B, and this is diathermic wall in between. We find that they are in thermal equilibrium with each other. What's the meaning of that? If these are constant volume gas systems and A and B are in thermal equilibrium with C, if you bring them in thermal contact with each other, their macroscopic variables will not change. That means their pressures will not change because they are already in thermal equilibrium with each other. This experimental fact is the statement of Zeroth Law of Thermodynamics, that if we have two systems in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. Now, we use the idea of thermal equilibrium to establish whether two systems are at the same temperature or not. So we have a rule in thermodynamics. Rule is two systems in thermal equilibrium with each other are at the same temperature, are at the same temperature. You need to remember this. Two systems in thermal equilibrium with each other are at the same temperature. So if systems are not in thermal equilibrium with each other, their temperatures are different. If they are in thermal equilibrium with each other, then their temperature is same. Now we move to the next topic. Our next topic is temperature scales. Temperature scales and thermometers. Temperature scale and thermometers. Now, using Zeroth Law of Thermodynamics, I can define a temperature scale. Idea is like this. If I have n systems, system 1, system 2, system 3, system 4, and so on this side also, these are my systems. Let they be constant volume gas systems. So I have n constant volume gas systems. Name them S1, S2, S3, S4, S5, S6, and likewise. I want to arrange them along a line in such a way that if I select some system, all systems to the right of this system are at a greater temperature than this given system, and all systems to the left of it are at a temperature lower than that of given system. I repeat, I have n systems, constant volume gas systems. I want to order them along a line in such a way that in this order, if I choose some system, all systems placed to the right of it are having larger temperature than the given system, chosen system, and all systems placed to the left of this chosen system are having a lesser temperature than this. This can be done using the idea already discussed that we bring systems in thermal contact with each other. If their macroscopic variables doesn't change, they are already at the same temperature, so they will have the same place in this line. Now if their macroscopic variables change, then they were at different temperatures. One was at higher temperature, second one was at lower temperature. Now if the pressure of system decreases, that means it is cooling because it is constant volume gas system. That means it was already at higher temperature. And if in thermal contact. If the pressure of a system increases, that means it is heating up. That means it was previously at lower temperature. This way, we can arrange the systems in this order, and we can use another property that if the temperature of system A is greater than the temperature of system B, and temperature of system B is greater than the temperature of system C, that will imply that temperature of system A is greater than the temperature of system C. This property we can also use that if TA is greater than TB and TB is greater than TC, that will mean TA is greater than TC. This way we can arrange these N systems. The question is, we want to define a temperature scale in such a way that means temperature scale means I want a method. I want a method of assigning a number to these systems, to these systems, so that greater number means greater temperature. Now I arranged these N systems in order. Now I want a method. I want to devise a method of assigning a number to these systems so that larger number means larger temperature. That is the meaning of temperature scale. Now what we do for that, for assigning number to these systems, how we develop our temperature scale. That is our next thing. So we know in SI system, we have 7 base quantities: mass, length, time, electric current, amount of a substance, amount of a substance, luminous intensity, luminous intensity, and temperature, and temperature. So temperature is one of the base quantities in SI system. You have mass, length, time, and is 3, electric current 4, amount of a substance 5, luminous intensity 6, and temperature 7. Now the measurement of these 6 quantities, excluding temperature, is different than that of temperature, because the nature of temperature is different than these 6 quantities. In these 6 quantities, what we do, we choose a standard, then make comparison. Now here, we cannot do that. In case of temperature, we cannot choose standard and then make the comparison, because the nature of temperature will not allow us to do that. We need to think over that. What we do in case of temperature. In case of temperature, we choose thermometer as our system first. Let this be some thermometer. Thermometers have various kinds. Let this be some thermometer. So it is my system, right? Then what we do, we use we use a material. We call that thermometric material. Thermometric material or thermometric substance means some substance whose which has some property which is function of temperature of the substance. That means it possesses a property which is called thermometric property. Thermometric property which changes if the temperature of the substance changes, right? So we select a thermometer. It is our system. Then we choose some material, some substance. The property of that substance is it has some property which changes if we change the temperature of the substance. That substance is thermometric substance and its property is thermometric property. Then what we do, for example, in case of mercury thermometer, we take a given mass of mercury, right? Given mass of mercury and put that mercury in this narrow tube, right? Then what happens? This mercury is our thermometric substance and its volume is our thermometric property. That means if you change the temperature of this mercury, you heat it, what will happen? Its volume will change, or I can say the length, this length of the mercury column will change, right? So we define the temperature of our system, this mercury thermometer, as function of the length of the mercury column. So we write an equation T is equal to A L plus B. Let this be my first equation. What's T? T is temperature of the mercury column, right? That means temperature of my thermometer, which is my system. L is length of the mercury column. Now what? This is the equation of a straight line. A is slope of the line and B is intercept. B is intercept of the line. Now A and B are unknowns. Now how can we solve for these two unknowns? Now what we do? Now before 1954, what we do, we select two states. One ice point of water. Ice point of water means that state when water and ice are in equilibrium at atmospheric pressure. Atmospheric pressure. Another thing is steam point of water. That is that state when water and vapor are in equilibrium at atmospheric pressure. Now, ice point of water is that state when water and ice are in equilibrium. Steam point of water is that state when water and vapor are in equilibrium at atmospheric pressure. This is sometimes called normal. This is normal. Steam point is called normal boiling point, and ice point is called normal melting. Now, this state we arbitrarily label its temperature as 0 degrees Celsius, and we label this state, the temperature of this state, arbitrarily as 100 degrees Celsius. I repeat, my problem was like this. I have n systems which I have arranged in such a way that if I select some system, all the systems to the right of it are at higher temperature, and the systems which are to the left of this system are at lower temperature. Now I want to define a mechanism by which I can assign number to these systems so that larger number will indicate larger temperature. For that I said we construct a thermometer. Now we took mercury in an arrow tube and defined temperature of the mercury thermometer, which is our system, as function of its length of the mercury column. Now we have two unknowns A and B. One is the intercept and second is the slope. To find these two unknowns, we pick two states, ice point of water and steam point of water, arbitrarily label the temperature of these states as 0 degrees Celsius and 100 degrees Celsius. And what I do, so I have equation T is equal to AL plus B. This is my equation. Now let Ti be the temperature of this mercury thermometer when it is in equilibrium with ice point. That means I have ice point state. I bring my thermometer in thermal contact with this ice point. It comes in thermal equilibrium with it. So it has same temperature at ice point. Likewise, I have steam point. So ice point state, I have steam point state. So when I bring my thermometer in thermal equilibrium with ice point, its temperature is Ti, and when I bring it in thermal contact with steam point, its temperature is Ts. So I note the length of the mercury column in both cases. Let Ni B, the length of the mercury column when my thermometer is in thermal equilibrium with ice point. So this temperature I have labeled 0 degrees Celsius. So I have got this equation second. Ti is equal to ALI plus B equal to 0 degrees Celsius. Similarly, I have second equation Ts is equal to ALS plus B, which I have labeled as 100 degrees Celsius. What is Ts? It is the temperature of my thermometer, mercury thermometer system, when it is in thermal equilibrium with steam point. Ls is the length of mercury column at that time. This temperature I have labeled arbitrarily as 100 degrees Celsius. Now I can solve. Solving 2 and 3 for A and B, we get A is equal to 100 degrees Celsius over Ls minus Li, and B is equal to minus 100 degrees Celsius Li over Ls minus Li. Now from these two equations, I can solve for A, slope, and intercept B, right? Then using this equation, A is equal to AL plus B, I can find the temperature of any system. For example, I have some system. I bring my thermometer in thermal contact with this. Note the length, put here. Now A and B I have already solved. Solve for T. That T is the temperature of the system. I repeat, I have some state from some system. I have to assign a number to its temperature. What I do, I bring my mercury thermometer in thermal contact with it. Note length of the mercury column, put it here. Now use the equations of A and B, put those values in the equation, solve for T, that is the temperature of this system. This way, I assign numbers to my n systems. So this is one way. Now, this is the equation of a straight line, as I have already told you. So we can graph it. So we are defining temperature as the function of length of the mercury column. So I have defined a straight line. Now this is my Li, and the temperature at the time is 0 degree centigrade, and if this is 100 degree Celsius here, this point is my Ls. Ls is the length of mercury column when it is in thermometers in thermal equilibrium with steam point. Li is the length of the mercury thermometer, mercury column, when it is in thermal equilibrium with ice point. This way we develop our mercury thermometer and define our temperature scale. There are other kinds of thermometers. For example, if I have constant volume V. Gas thermometer. We know in constant volume gas systems, change in pressure indicates change in temperature. So our thermometric property here is pressure, not length. Our equation will be this way: A P plus B. P is pressure in the gas thermometer, T is temperature of the gas in the thermometer. And similarly, when we use two reference states as steam point and ice point and label their temperatures, we can solve for A and B. Here A will be 100 degrees Celsius over S minus Pi, and B will be minus 100 degrees Celsius Pi by Ps minus Pi. Now what is Ps and Pi? Ps is the pressure in the gas of the thermometer when it is in thermal equilibrium with steam point. Pi is the pressure in the gas of the thermometer when it is in thermal equilibrium with ice point. So then this thermometer can also be used to assign numbers to our N systems or any system. You have to bring your thermometer in thermal equilibrium with that system, record the pressure in the gas, use value of A and B from these equations, solve for T. So that T is the required temperature. There are other kinds of thermometers also. For example, there is electric resistance thermometer, where we define the temperature of the resistor as function of its resistance. Question is, when we use these different kinds of thermometers to assign a number to some system for its temperature, will these different kinds of temperatures agree or not? That means when I have these systems, I have to assign number to their temperature. If I first use mercury thermometer, it will assign some number to the system, some number to the system, some number to the system, and so on. Then I change my thermometer. I use the constant volume gas thermometer. It will assign some numbers to these systems. Then I use some other thermometer. It will assign some numbers. Will these numbers will be same or not? That means number assigned to certain system by one thermometer, other thermometer, third thermometer, will they agree or not? Numbers will differ or not? In general, they will differ. They differ. That means there is disagreement between these thermometers. They will agree only on ice point and steam point. They will disagree for all other temperatures. And discrepancy is large if the temperature to be measured is far from 0 degrees Celsius and 100 degrees Celsius, which are our reference states. So there is disagreement. But there is one group of thermometers called the gas thermometers. Gas thermometers. They can be constant volume gas thermometers, or constant pressure gas thermometers. In constant volume gas thermometers, we define temperature as function of pressure, and in constant pressure gas thermometers, we define temperature as function of volume. Now, these gas thermometers agree, provided the pressure of the gas in the thermometer is not too high and the temperature of the gas in the thermometer is not too low. I repeat, in general, all the thermometers disagree, but if we take only gas thermometers, all thermometers disagree. But if we take only gas thermometers, they agree as long as the pressure of the gas in the thermometer is not too high and the temperature of the gas in the thermometer is not too low. We will continue this discussion. I will give you homework first. Your homework is simple question. Question is 10 objects have the speeds tabulated. So this is my table. This is speed in meter per second. Is 2, 5, 6, and 8. This is 3, 3, 3, 1. This is number of objects. Question is calculate their RMS speed. RMS stands for root mean square. I repeat the question. 10 objects have the speeds tabulated. I explain this table. This means 3 objects have speed 2 meter per second, 3 objects have 5 meter per second, 3 objects have 6 meter per second, and 1 object has 8 meter per second speed. So in total I have 10 objects. Their speed is as shown in the table. I have to calculate their root mean square speed, RMS speed. So try this question, it's easy. This is all for today. Thank you and work hard.